Population density. Exactly how dense will a population be, and how many organisms can occupy a certain unit space? There's also review time being used here at the end of a bit of a unit. Be able to define rarity, be able to define population density. Simple. Be able to relate organism size to population density. Compare the 7 different forms of rarity and 1 form of abundance. Explained by many commons are known as uncommon, and apply population density concepts to real-life examples. Why don't you come with me to the garden? Population density is directly related to organism size, and nowhere is this more apparent than when trying to plant a garden for maximum yield. All right, maximum effort, maximum yield. Here we go, down to the level of the carrots. What we see here is above ground a lot of competition going on between different carrot plants as they all try to get the maximum amount of sunlight. Now I did put some buckwheat up above them, but enough sunlight gets through for the carrots to enjoy. Below ground, you can see them growing very close to one another with that much below ground tissue and this much above ground tissue. They're deeply in competition, but obviously still doing just fine. So that's a snack. Other plants, though, may require a lot more space. These big squash right here, very large plants, good yield, but I can only grow 4 squash where I could probably grow at least 20, 30, 40 carrots. And I could grow even less. Getting dirt here. I could grow even fewer trees. So here's the forest behind me. And as you see, the amount of space taken up is bigger with bigger organisms, thus leading to a lower population density. And that's very obvious with plants, where population density has to do with how much sunlight they can get. With animals, it's a little more complex because they have certain food and nutritional requirements, but it's the same idea. The bigger the organism, the more the needs, the less dense a population will be. Yeah, intraspecific competition. Delicious. Well, that is crisp. I watched it. If you're following all the videos, one question might be, did the carrots and the potatoes actually end up making more? I got 39 pounds of potatoes, and I've got 1 gallon of frozen carrots, and I've still got probably 2 gallons of carrots living in the soil still. The carrots probably 1 out per unit area. So, yeah, they 1 out per unit area. One reason for that was intra-specific competition, which was determining the overall density of the organisms. An interesting fact is, as far as density goes, like if we're talking nutritional density, then carrots and potatoes are going to be almost on parity. This is obviously higher in vitamin A, and potatoes are higher in certain other minerals. But I mean, overall, if you want to get nutritional density, they're pretty close. Population density, though, really depends on the size of the organism and how they're competing with one another. Now, the potatoes above ground were huge. They were just these bushes. Below ground, there was a whole bunch of tubers, but they were actually relatively well spread out. And the carrots below ground is just a spike, and above ground are all those leafy greens that I've been showing you. So that's competition. Here's some competition, some sagebrush too. So you see down here, you've got over there what you would expect with sagebrush if each sagebrush was a circle. Below it was where all the roots were. Well, someone with a lot of time on their hands ended up digging this up and found that there was a lot of competition such that they actually mostly avoided one another. There's not much overlap between the different sagebrush roots. Just as if I were to go underground, when I was digging up the potatoes, if I hit a Yukon Gold, then I know that the next 3 or 4 potatoes I'm likely to find are likely going to be Yukon Gold. Whereas if I find a purple potato, it's going to be sitting with only other purple potatoes in the same plant. They're not intermingling, much the same way as these creosote bushes. We're not, sagebrush, creosote, one of those two. We're not intermingling. And much the same way, these packs, these wolf packs, In Wyoming, we're not intermingling much. There is some range overlap, but they try to avoid that. Generally a good practice. So they try to avoid range overlap because they are competing with one another, but that is going to determine the population density as well. And it's also a factor of size, as you saw in the garden. So the zucchini were very large plants, and they took up, they could only be at a certain density, at a much lower density than the carrots. Zucchini, squash, I had both. The Douglas fir trees were at a far bigger mass, lower density. And this is pretty much just a straight up correlation, plain and simple, both for herbivorous mammals and for plants. The bigger the organism, the more resources it uses, and the less you can have as far as density goes. Now, there is a variation within birds, within invertebrates, within mammals, and within birds, invertebrates, mammals, reptiles. Yeah. So the aquatic and the terrestrial ones have similar disagreements, but you'll see that they overlap pretty well with this line, this linear relationship, with many aquatic invertebrates living actually at a slightly higher population density than expected, but not much higher than the overall line. There are mammals that have a higher population density than birds. This could be possibly due to the lengthier care of young and the tendency to live in herds or packs. But other than that, it's just a size deal. All right, rarity and abundance. Seven forms of rarity sounds difficult until you actually start looking at it. Go for a walk. Just you can hit pause on this and go for a short walk and just notice what animals and plants you see. Go on, get outside a little bit. Welcome back. Hoping you didn't just stay. Some animals and plants are more common than others. You saw that. You probably looked around and saw that there was some things dominating the landscape, and some that you only saw one or two. So what does it mean to be common, and what does it mean to be uncommon, and what does it mean to be rare? There are 7 ways to be rare. We have these 3 different traits. You have the extensive geographic size, you have geographic size, habitat tolerance, and local populations. When you have three factors, they can either be good or bad. So you can have an extensive population range or a geographic range, or a restricted geographic range. So it's either extensive or restricted, 1 or 2. Either a broad habitat tolerance or a narrow habitat tolerance. Either a large local populations or very small local populations, like if you're a bigger organism. So we've got 3 things and 2 possibilities for each. So that's 2 possibilities to the third. So to the third is there are 8 possible outcomes. And you can be common only if you have all 3 in the positive way. You're uncommon if you have 1 or 2 in that range, and really rare, if you have all 3 in the negative range. So mountain gorillas are very rare. And then you have the Pichicardia. Yeah, that's so rare they couldn't even draw a picture of it. You can look it up online. It's not like there aren't photos, and it's not like they took photos. It's such a misleading graph. Disappointing. Anyway, 7 forms of rarity just means there are 7 different ways to be uncommon or rare. And it can be whether restricted geographic range, a narrow habitat tolerance, or small populations. Any one of those 3, and you're uncommon, and all of those 3, and you're rare. So let's think about looking for species. Grab a pen and a pad and go for a walk and check how many species you see. Record how far you go. What's going to happen is, you know what, maybe just go for the walk first. So I saw an oak tree, check. Saw a maple tree, check. Saw a Douglas fir, check. Next step, see if you can walk, and then see as you walk how many new species are you encountering? So if you want to actually take this time to actually do this, I'm offering you 2 walks in one day. Go for it. Welcome back, or most of you probably said 1 walk is enough for me, or 0 walks, or you're reviewing this. So really what's going to happen, though, is the farther you walk, you're going to always be encountering new species. But you're going to get most of the species in a short amount of time. All the common species will be visible in the first couple samples. All of them. All the common species. All of the top here. The uncommon species will be found sooner, and then the more uncommon found later, and then the rare found only very rarely. So eventually it does level off. You almost certainly won't ever find all the species. Species area curves here, one interesting facet is that you don't find all of them. It's some of them are cryptic, some of them are season specific, some of them are migratory. So it can take a very long time to find everything that lives here. I mean, if you're going to Pokemon the native flora and fauna, you should probably stay around for a while. I'm still encountering the occasional new species. So it'll almost level off, but it won't ever completely level off. But really what you're getting is it will level off. And when it does, you've got most of them. So you can get all of the common ones, uncommon ones, mostly uncommon ones, very uncommon ones, and some rare. You've probably sampled most of the species in an area. And yeah. So I want you to apply this. This is what we're doing in class. This is an activity. Find an organism living in the Pacific Northwest using your thinking cap. Figure out if it's a common, uncommon, or rare using those 7 different types of rarity and 1 type of common. And then present and describe it to the class. That's kind of fun. I don't really know if I'm going to make a forum for this. Describe population size and the density of the organism, how you find a certain density compared to the organism's size. Douglas fir are very common. You can't use this one. It's got a broad geographical range. It's got a pretty broad habitat tolerance, and population sizes are huge. So population sizes are huge, but they aren't super dense because these are very big organisms. There we go. Now reviewing, here's the fun part about doing these videos is just go watch the other videos. If you have questions, just fire them right back at me by email or hit me up on Zoom office hours. We're going to review this in class and spend some time hammering through, but you can just go check out the YouTube videos. So have fun. You know what? Maybe go for another walk too.